Okay, so how would this update actually look like? So we can define this update using gradient ascent steps, right? So we set the score for a given action, the action that we just took at time step t. We update the score for this action using the existing score for this action plus the gradient. We take a small gradient ascent step on for that action. Now the gradient ascent step will provide us the direction of update to the score of 80 such that the probability is increased. But we don't necessarily want to increase the probability, right? When should we increase the probability?
Well, when an action's reward is higher than the average reward I've been getting from the other actions.
Or for some baseline. Let's say we have some baseline reward saying, listen, this is a baseline reward. If you get a bit higher than that, good. If below that, well, you can do better, right? And so you're right. This is exactly the term here. So RT is the reward that we observed at the current time step t. And let's say that RT with the bar on top, that's the baseline, right? You want to do better than that. And so you can see that if the observed reward after taking action AT, at time step t, is better than the baseline, then the gradient step becomes positive, right? We're taking a gradient ascent step. However, if the observed reward is below the baseline reward, we'll take a step in the other direction. That is, we'll take a step that decreases the probability of choosing that action, right? That action AT, the one that we just took. Also, alpha here is the learning step, as we've seen previously. Okay, just a hyperparameter. Okay, so this is the update of the score that we assign to the action that we just took at time step t. Any idea what this is? The other line?
Well, it seems to update the scores for the other actions apart from the action that we took at time step t.
And how would we like to update those actions? So, say for instance, you know what? The same scenario as before. Let's assume that the reward that we saw is above the baseline reward. That is, looks like a good action to perform. How should we update the score for all of the other actions?
Well, I guess I would want actions which are as good as my current action to not be changed, and the actions which don't score, which score below that baseline to get a lower score.
Yes, but we're doing reinforcement learning, so we don't know. I mean, that's the Q star values. It would be nice if we know what are the score that is affiliated, what score should we expect by playing each one of the actions. But for now, for a single step, for a single time step, we played the specific action and we said, we're happy with the results. This action was actually better than the baseline, better than what we expected. Okay, so the first line right here, or here, increases the probability of taking that action. And what's happening here? So here, for all of the other actions, that are not the one that we just chose, we do a very similar gradient step, right? Where we update the score for these actions based on the reward that we just observed. If we observe the reward that is better than some baseline reward, then we follow a gradient ascent step that, or we ask the question, how do we change the score assigned to any one of these actions, to action A, such that the probability of AT is increased, right? The action that we just chose. So actually both of these equations are doing the same thing. Both of them are either increasing or decreasing the probability of choosing the action that we just took, AT. So increasing or decreasing based on the reward that we observed, if it's a good reward or a bad reward. Okay? But we update the scores for all of these actions. So what do we have here? We update the score based on observed rewards and baseline rewards, right, as we just discussed. And so this is just the sanity check that we just discussed. If the observed reward is larger than the baseline, so seems like a good action to take, we increase the score of the chosen action, 80, and decrease the score of all other actions, right? All of the actions that are not 80. Else, that is, if the observed reward is lower than the baseline, we do the opposite. Makes sense, right? Okay.
Yes.
Any questions?
But over here, if I had another action, which is just as good as action 80, would we still reduce the scores?
How do you know that it's just as good? Right? Well, I mean, how do you measure that? You don't have the Q values. I mean, you would like to have the Q values, right? The Q star values. You would like to know how valuable each action is, but you don't. This is reinforcement learning. You can try them and you can observe the reward, right? And the reward might seem good or seem bad, but right, you cannot answer the question of, hey, I tried an action, how do I know if it's better or worse than the other actions? Well, you'll have to play them and converge over time, right?
I had another question. Does decreasing the score of the other actions also necessarily decrease the probability of taking that action? Is it a direct correlation?
So if you decrease the scores for all of the actions, depends on the magnitude. It's a bit. Eventually, you can think of it as you cannot decrease all of the probabilities, right? Because the probabilities eventually sum to 1. Or with the softmax function, it might reshape the proportions between the probabilities. So I don't have a straight up answer to your question. However, if we have a situation like this where we decrease the score for all actions but one action, yes, in that case, the probabilities for the other actions will decrease, while the probability for the actions that you didn't change the score for, it will increase, right? Okay, so one last question that we need to still figure out is how do we actually define, or what are the derivatives, the partial derivatives of the probabilities for each one of the actions, or for a specific action that we chose AT, with respect to the score values, right? That's, well, we still need to answer that, and that's not necessarily trivial, not very difficult, but not trivial. We'll have to do some math. Okay, so let's do that. Let's compute the softmax derivatives. What we would like to compute is the how to change a probability of a specific action. So here I changed a bit the notation here. So instead of P of AI, I'm just using PI, just for not to overload the screen. Okay, so PI means the probability of action I, and same goes for AGI. AGI just means the A score for action I. Okay, so just more concise notation, but I didn't change anything conceptually. So the partial derivative for a probability for a specific action I with respect to the score of any other action or the same action J, so J and I can be the same, we have to compute also that, is defined as follows if we use a softmax function, a Boltzmann distribution, right? So this is just the definition of the probability based on the Boltzmann distribution as we saw it just before. The way we're going to compute this partial derivative is using the how did you call it? The
division rule.
The division rule
of differentiation.
In any case, I just included it here, the exact definition of this rule. We're going to use this rule, where here the rule on the right here is defined with respect to fx and gx. So in our case, f would be e of to the power of hi, and g would be the summation of e to the power of hk for all of the actions. So these are our f and g's, and now we can compute our derivative. For the case that ai equals j, when do we need this case? Do you remember?
When this is for when we want to increase change the probability of the action chosen. Correct.
Right, so when we update the score...
Score, sorry, not the probability, the score.
Yeah, we cannot control the probabilities, we can control the scores, which are, when you pass them into a softmax function, result in a specific probability, but we cannot tune the probability directly, okay? So, for the case that I equals j, that's the first line that we had, when we want to update the score for the action that we actually chose in order to decrease or increase that probability of that action. Right? So if I equals j, we can write our expression as follows. It can be seen here, right? Using the division rule. We can further simplify this expression, okay, by dividing it into 2. And then we can restructure or use the definition of g and e to the power of hi, which is exactly the definition of the probability of taking action I based on the softmax distribution. And so we can simplify this expression to pi, the probability of taking action I, times 1 minus the probability of taking probability pj. Or if, in the case that I and j are the same thing, we can just define it. We don't need to define it with respect to both pi and pj because, well, they are the same thing. Okay, so we can say that this is either pj times 1 minus pj or pi minus 1 minus pi. Okay, it's the same here. Now we also need to define the derivative. So as you can see, this is a very simple derivative, right? That can be easily computed. Just we can take just the current probability for the action that we just took. We just need that value in order to define the derivative in the probability with respect to the score. So this becomes actually a very nice derivative, or the softmax function, the Boltzmann distribution, has a very nice derivative to it, and a very simple one. Now we still need to compute for the case that I is not equal j, right? For the case, how do we update all of the actions that are different than the action that we just chose? So again, this is even simpler. This results in 0 time g minus e to the power of hi times e to the power of aj over g squared. And again, we can simplify that as minus e to the power of hi over g multiplied by e to the power of hj over g, which is right based on the softmax probability definition. It's simply pi and pj, right? So it's minus pi times pj, and in this case, pi is not equal pj. So this is the derivative in this form. Okay, now we know how to change the scores of both the action that we chose and the score for actions that we don't chose in a way that increases the probability of taking the action that we chose, action I. We don't always want to increase that probability, right? Sometimes we chose an action and we saw, well, that's a bad action, so we'll take a gradient descent step. We'll take a step in the other way, right? And that's the r minus r bar that we saw previously. That will tell us in which direction do we want to update those scores. Question?
Yes, Professor.
Yeah.
I had another question about the update for the other actions, action not selected. Is it possible that there is an action, maybe which would get an even higher score than the action at time step t, but by updating its score here, it might reduce the probability of the better action, because that sounds, maybe it might be counterproductive towards learning.
I see what you mean, right. So, okay, so let me reiterate your question and tell me if I understood correctly. So you're asking, what would happen if, so I know I'm starting to converge on a good action, let's say action number 1 seems very promising, but I always have some probability of choosing also bad actions because I'm using a softmax or a Boltzmann distribution. And let's say I randomly chose with low probability action number 3, which is worse than action number 1. However, for some reason I got a very high reward for it. meaning very high reward, better than the baseline reward, better than what I expect so far. So A3 seems very promising for at the current time step. So you're saying, no, I might update the score value to action number 3 to be higher than action number 1.
Yes.
So that might happen, specifically as you just took action number 3 and it seemed to have a high score. So I actually want it to happen in some sense. And if you're saying that, listen, the rewards are very noisy, so that was just a strike of luck. And I don't want actually to improve A3 or to set A3 to have a higher score compared to A1. In that case, I would say you have a very noisy reward distribution, reward function. Then you should set your alpha, your learning rate, to be small. Okay? That means that you don't start jumping around based on some random reward that you see. So if you keep your learning rate, the alpha, small enough, then the update will be, well, slow and over several samples, and that will allow you to mitigate very noisy reward functions. Okay? If that makes sense.
I have a follow-up question. Could you go to the previous slide? So,
1 second. Right.
yeah, so in the case where the current action is higher than this baseline, right? Suppose RT is higher than this baseline.
Okay, the current reward.
Yes.
Okay.
The reward that we see in the current time step, suppose it's not a noisy reward.
Okay.
And we always get RT, which is above some baseline. But suppose there's another action which at the same time step would have given me some value greater than RT.
I see what you mean.
So now, would I still reduce the scores and the probability of that action?
It would. So
even if it's not noisy.
What you're describing is something that is more relevant at the initial stages of training. And it sounds like you're saying, hey, listen, if I have my baseline reward badly initialized, I initialized it very low. Every action that I choose seems to be a good action, right? And then I'll start increasing the scores for actions that they're actually quite bad. And I want to avoid that. So that might be an issue in initial stages of the training. Over time, of course, the baseline reward should, if you set it up, for instance, as the average of all the rewards that you see so far, it should converge on something meaningful. But you're right. So this might be an issue. So the question of how do you initialize your baseline reward, what you expect, is an interesting question. And this also ties back into something that we've seen previously. You might want to say, well, I would like to use what's called optimistic initialization, right? I'll say, I expect all rewards to be very good, and then you'll start sampling and everything looks bad, actually. And then you'll start pushing things downwards, which is good for exploration. We saw some results for that. So the same idea with optimistic initialization can also apply here for setting the initial baseline reward. We'll see some results later on regarding different ways to set up the baseline reward.
Thank you.
Sure. Actually, it's quite an important question in also when we move later to the more general reinforcement learning and general MDPs, there's also the notion of how do we set the baseline reward, and we'll see some ways to do that, including some actocritic approaches, like more advanced approaches. Okay, so we've seen that. Where are we? Okay, we derived that, actually. So let's move on to define a loss function for the softmax derivative.